gonna talk
Nee,
about...
nee.
I'm gonna talk about logic gates.
Dit weet je.
And
Yes.
logic gates are really cool. I'm just gonna show you something. What do all of these things have in common?
Logic gates.
Oh.
Huh? They all talk one language. And this is this one.
Oh.
Baldur's Gate 3 has 1.2 trillion of these ones in a file. That's the entire game, nothing but this.
That's my cookie.
And these things are also can look like this. This is like a human way of seeing the ones and zeros. And I can explain what they do. So to control the ones and zeros, you have to be able to change them. So if I have the two zeros here, or the off signals, you can also think as 0 as off and 1 as on. On the top here, we have two off signals. But if I switch them on, so that's 1 now, and this is a 1 now, it sends a signal, because it's an AND gate. It only sends a signal if both of the signals are on. So if I do this, it doesn't send a signal. If I do the other one, no signal. And that's one of them. The other one is an OR gate. And if I do one of them, it turns on. If I do the other, it does. And also if I do both. Beneath that one, it's a NOT gate. It inverts the signal from being on to off or off to on. And this seems so simple. How can that make so much complicated programs like Snapchat, Instagram, everything like that? How is that possible? If you combine them in clever ways, you can get any result ever, basically. So this is a very simple thing. It changes one thing about the OR gate. So this is basically that one, just I have made a little change. If I send one signal, it sends a signal. If I do the other one, it does. But if I send two signals, it stops sending a signal. And it sends first signal to OR gate, which continues through the AND gate. But if this detects that there are two signals, it goes into a NOT gate, converts the signal, and deactivates the AND gate, deactivating the power. So that basically does that. And another way to visualize this is like this. This is called a truth. I forgot it. Kai. Good. Truth. Okay, never mind. I don't remember what it's called, but this just shows like, oh, if you have 1 and a 0, you get a 1. 0 and 1, you get a 1. Like all of these. This is the boring way of looking at it. So we continue on to next step. Like let's count in binary. Binary is a number system, just like the normal numbers we use, because we count like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we use 10 different numbers, all from 0 to 9, to explain numbers. But in binary, we just use 2. So instead of if I am boring and you want me to move on, just tell me.
This is your time.
It is my time. Instead of writing 1, we just write, we start at 0, so we just start at 0. Nothing. A 1. And then we do something interesting. We do a 1, 0. This looks like a 10. It's not. This is in binary. And if we want to do a 3, we do this. A 4, we do this. And the pattern is not that intuitive. I know it's a bit hard to understand, but I will explain it further when we get to some stuff I have made. Next step is 1, 0, 1, 1, 1, 0, 1, 1, 1, 1, 0, 0, 0. I don't know if you all get it. Some of you may, and most of you probably don't, because explaining binary is hard. You have to like kind of learn it by thinking of it yourself. But this is how you count to, wait, let me count to 10. That's 10 in binary. 1, 0, 1, 0. And the way of thinking of this is you have the places. You can think of, the way you think of like the first place, the 10th place, and the 100th place in our number system, our regular one, you can think of as 1, 2, 4, and 8, and 16, and 32, 64, 128, you know? So if you do the number 10, 0, 1, 0, 1, we can just add 8 and 2, and that's 10 in our number system. That's why that is 10 here. And we can do that with a lot of stuff. I don't have time to like actually teach you. I have to just show you really quickly because I have limited time and I want to show you things that I have made with logic gates.
Anne, excuse me, but that 1, 2, 4, 8, it's always like a double.
It always doubles.
Okay.
1, 2, 4, 8, 16, 32, 64, 128, 512, no, 508, yeah, and on until you get like 2048. This is like a popular game. Truth tables is that thing. That's the small machine I made earlier. It's the X4 gate or exclusive 4 gate. Adders. Okay. I think we will like half skip this. I'm rushing it because I have like 5 minutes left to do like everything else. But it's basically small like machines made of the logic gates that do math. So if you look here, if we add 2 numbers, so if this is off, this is on, you get what's called, for the 1, 0. It's inverted here because the carry is here, where you carry numbers. I will show you an adder later. Okay, I have 5 minutes left, so I'm just gonna go fast. First, I'm gonna show you something that does math. So let's go. This looks complicated, I know, because it kind of is. All of these things that says other things than and or not are basically just made up of the things. So inside these ones are these ones. You get that? It's a mess of logic, and the thing is that I am not that smart, so I have done everything overcomplicated and weird and not right. But I can plus 2 numbers together. So if I do number 5 in binary and the number, let's see, number, this is 4, we get that number, which is 9. Yes. I have just made it weird. From here and down is you can type a number, and from here and up you can type a number. Here I typed the 1 place and the 4th place. That's a 5, and here I took the 4th place. That gives us 1 on the 8th place and 1 on the 1st place. So that's a 9. I'm gonna get to more fun stuff now. I'm just gonna jump right into my magnum opus when it comes to this type of stuff. This monstrosity. You can type in a number, like the number 10. It shows you a 10. And the reason why this is so hard to do is because these are 7 segment displays. If you power the top one, you power the thing in white, you know? So you cannot put a binary signal into this. So this thing translates 3 different, like a big, like 100, like a number up to 100, into 4 different 4-bit binary signals, and then converts that into this. So the thing that happens when it gets into here. Okay, by the way, before I explain this is not the right way to do it. This is how I did it. So don't think this is not the way you actually should do it. I don't know how you should do it, because I did it my way.
Hell yeah.
So the first thing this does, I'm gonna go into them afterwards. It takes this number, it goes into here, and then this says, okay, are there any numbers over 100? And if there are, if the number is like 210, it subtracts 200 from it, and then sends a signal here that yes, we have 200s. then it goes into here, and it finds out how many tens there are, removes the tens, and then sends signal how many tens there are. And then it just sends the normal signal. So I'm gonna go and just type a really big number, 255.
Yo.
And then I'm gonna go into this. Ignore the brown ones, because they do something else that I'm gonna explain afterwards. So yeah, you see here, big number comes in, and it removed, if you see the what's powered, it removed 200. It goes into here, and then you just have the ones places. And let's see here, go for my time, I have no time left. This is, yeah, I have like no time left. So it goes really fast and really complicated. This is spaghetti, basically, because I have done a lot of weird stuff. It's a lot of stuff. But if you go deep enough into everything of this, you'll just get normal logic gates. This one is the worst one.
Oh!
It's insane. That is 20 of those machines, and inside every single of those is this thing and more math.
Yeah.
And by the way, I just looked this. The green one says Hamming weight. That's not what it should be. It's just something so like adds numbers together. It has nothing to do with that word. I don't know why I called it that. So yeah, and if you this one, okay, this one looks bad. I promise it's not. It's just really overcomplicated. Every single, it's like 10 different machines in this thing. So every one of like this is one thing. This is one thing. This is one thing. And all of them just check what the signal is. So if this is off, this is off, this is on, this is off. It goes into all the machines, and only this one sees that, oh, these are 3 that I want off, and this is the one I want on. So it sends a signal into this one. And every one of them do that. So only one activates. And it doesn't do numbers over 9. And then it goes into this. Still a mess. This is to fix the problem with like if 2 wires go into one thing, like and then this one. If this is on and this is off, this will start glitching. It doesn't know what to do because it gets an off signal and an on signal. That's why you use OR gates. And this is just a lot of OR gates put together. I hope something of this makes sense. And I can also switch kind of what program I use. So if I press this button, I switch kind of the program. You didn't see that, but this turned blue, this turned black. And that's because these 2 got activated. Okay, this one goes up here. It's a NOT gate, so it doesn't, so it deactivates this. This sends a signal and activates this. And this is kind of a clock. So if I just reset the signal, just have to do deliberate stuff. If I do this, it starts counting. What is it? It starts counting a binary. 3, 4, 5, 6, 7. And you can see here the binary number going in. And this is a quite large number, so it goes into this, gets subtracted, gets turned into 3 different binary channels. Makes this. I can show you the inside of my this thing. And after this, I'm done. I promise. So this basically just this is a timer kind of, has a clock. This is a binary counter. So this just counts in binary, basically. It looks complicated. It's a bit complicated, but not that much. So yeah, that is basically what I wanted to talk about. I went really fast through everything because I didn't have enough time at all. This is like, to explain this correctly, you should have like 3 weeks of lessons. And I had 15 minutes. So yeah, that's all you get. Hi.
So you did this all studying by yourself, like, or did you go for classes for this?
I have not. I went to a Christian school. I did not
Holy
learn
shit,
anything.
yeah. Crazy then.
I learned everything by myself. Yeah. YouTube.
That's
YouTube is awesome.
yeah.
Yeah.
You know.
Why is it like why does it go up by like 1, 2, 4, 8? I don't know, like why are those the numbers?
Because if we try to count it in binary, you start with 0. We can do here. I took that away. I start with 1, right? And then I go 1, 0, and then 1, 1, and then 1, 0, 0. And to get to, I can. I don't know how to. I don't have stuff to explain with it, but it doubles because of the way you count in binary. You just do every single combination of zeros and one until you get to 3 different numbers, and then you do all the combination of that until you get to 4. So then the numbers of combinations of ones and zeros within those digits doubles for every digit you add. So that's why binary is so good, because every one of these doubles it. So a 4-bit number, the maximum amount you could have is 15. But for an 8-bit number, the highest number you can get is 255.
This isn't a question, but I feel like you would vibe with my brother. This is just my home.
Hello.
Listening to this.
Putting on my nerd glasses. So yeah, any more questions? Nina? No, Sarah.
Nina.
I saw a hand between you. I wasn't sure.
Wait,
Yeah.
what was the ad that you were using?
It's called Digital Logic Sim. If you go on YouTube and search digital Logic Sim, you will find a YouTube channel that's make tutorials, and he made that program. So go on YouTube and check it out. Any more questions? I saw you had a hand up.
Jeg skjønte ikke noe.
Okay.
Men jeg kan spørre for en venn.
Of course.
Ja. Får vi dette på prøva til uka?
Ja. Det er prøve. It's
Vi må lese.
this is on the quiz tomorrow. So if you haven't studied, yeah, your fate is.
Nei, men hvor det var jo egentlig skikkelig nerdete, men det var jo også ganske morsomt. Så jeg lurer på hvorfor interesserer det her deg?
Okay, the reason this is interesting to me, not the cats, the logic, is that everything is made of this. Like, you can think of in physics, everything around you is made of atoms, but in computer science, everything is made out of logic gates, kind of. So it's the atoms of the computer world. So anything, like any game, any program, any calculations, and like on your phone, everything you ever do online or digitally is made up of zeros and ones and logic gates.
Så det er computernes svar på atomer og molekyler, da?
Ja.
Ok, takk. Godt svar.
So yeah. Any more questions, Kai?
How long did your magnetist take to kind of get right and troubleshoot?
Oh my God, the big program, the one I counted.
Yeah.
I didn't do school. I just
Exactly.
got to school and did this on my computer, went home and did the same. I didn't do school. I just did that for like a few weeks.
That's impressive.
And the thing is that I learned everything myself. So when I got to a problem, I was like, oh, this is impossible. Then I had to watch YouTube for like 3 days continuously, and then I'm like, oh, it's that simple.
Because it's even, we're not like doing my computer science, but like you don't go that in depth into making.
Yeah,
like, what you're making.
I started making an actual computer with like buses and like registers and stuff. But I had
really
to
cool.
also do school,
Yeah.
so I didn't have time. So yeah, but that is really interesting. Like people that make like computers in Minecraft and stuff. I always love that, and that is basically
They're
logic
using
gates.
logic
Just
gates,
you
yeah.
just use redstone and blocks and stuff.
Exactly.
That's really cool.
But like,
Do you want me to shut up now, or should I?
We love you.
You were talking. I
no,
interrupted you.
I was just saying like just the whole system, like, it's kind of, that's really cool.
Yeah. It's like programming physically, kind of. With logic gates, programming physically, because the ones and zeros, in reality, when you go in programming stuff, you see it in Python. Like you see print parentheses, this thing parentheses, and that's how you look at programming. But a computer doesn't see that; it just sees ones and zeros in like trillions of them. So yeah, be glad you're not a computer, because reading is boring if you're a computer. 0 1 0 0 1 1 1 0.
Tusen takk, Anna.
Woo!